The recording, and there's my audio. All right. Get out from under my chair without falling over. We did the lab yesterday. We did on capacitance. So today we're going to look a little more formally at capacitance, and in particular dielectrics, and how we will even look at how to derive that formula, that equation we used on calculating capacitance, at least between parallel plates. As soon as I clean up after that's that guy. We've already looked at E fields and potentials, such. Coulomb's law. We've looked at Gauss's law. I take it everybody's up to speed on those. Yes? No? Okay. When you put charge, you put a conductive surface inside an E field, you understand how it will induce. It'll draw oppositely charged particles, electrons or protons, to itself, create the separation. Well, you have two plates. And you apply a voltage to them. Your negative and positive voltage. This plate, this side is going to draw electrons out of this plate, leave it positively charged. This side is going to push electrons to the plate, leave it negatively charged. Now, the question is, how much charge is going to be put minus Q on one side of charge, that minus Q coulombs of electrons on this side, plus Q coulombs of positive charge on this side. Notice I did not put Q over 2. Right? I didn't say half of the charge is here and the other half is there. Because if you add those two charges together, minus Q and plus Q, what do you end up with? 0, a net neutral charge. Okay. If that is V volts, and that many volts, let me see. How do I want to write? Yeah. I'm going to put it the way it is in the book. If you put that many volts across that much capacitance, this is how many coulombs of charge it's going to store on both plates, oppositely charged, but it will move Q. Okay. Let's talk about this in terms of numbers so that I don't sound like I'm babbling. If you have 1 farad of capacitance, how many of you have ever seen a 1 farad capacitor? How many of you have worked with capacitors, electronics? What? Okay. Typically you find them in microfarads. Yeah, because up until very, very recently, no such thing as a 1 farad capacitor. Maybe about 10, 15 years ago, they kindly came up with 1 farad capacitors, but up until 10 or 15 years ago, there was no such thing. Microfarads, picofarads, that's what you dealt with. But the units were still defined in this way. 1 farad of capacitance. If you put 1 volt of potential across 1 farad of capacitance, you will have 1 coulomb of charge. Or more specifically, you'll have minus 1 coulomb of charge on the negative plate and plus 1 coulomb of charge on the positive plate. So, this is where we got the definition. You can see the capacitance was defined as 1 farad was defined as 1 coulomb of charge per 1 volt of electricity. Okay? Now, that's how all of this is defined. Let's keep that little equation right there because it's going to come in handy here in a minute. Then I want to back up a little bit. And let's go back and look at Gauss's law. If we wanted to draw a Gaussian surface and do the calculations, what would we discover? The sum of the perpendicular E fields times the change in area would be equal to the enclosed Q divided by epsilon sub naught, right? Well, when we sum up all of these little delta areas and all of the little chunks of E field perpendicular to each one of them, we end up with the E field times the area is equal to the charge enclosed divided by epsilon sub naught. All right, that's just Gauss's law. And for the record, that would apply to any arbitrary shape of conductive surface. All right? Now, come back to our capacitance. We've got capacitance times voltage is equal to Q, the total charge. Or capacitance is equal to the total charge divided by the voltage. Well, what is the voltage? Here we've got E times the area is equal, and this is going to get real messy real quick, so I'm going to move over here. We've got our E field times the area of the conductive surface is equal to Q over epsilon sub naught, which means our E field is simply equal to the charge divided by the area times epsilon sub naught. Everybody with me so far? Okay? It is. It's the total charge. I've just extended the Gaussian surface over the whole parallel plate. Okay. Because remember, we don't need to worry about fringing effects here because this applies to any arbitrary conductive surface. All right? So, that's the E field. What is the voltage? How do you get from E field to potential, to the voltage. E is what? No, K Q over R squared, or over distance squared. V is K times Q over D, which is equal to E times D. That's what you get if you multiply E times D. See what I'm saying? So, if I want to turn this into a voltage, I multiply both sides by D, and I get E times D equals V equals Q times D over A epsilon sub naught. That is my voltage. But my capacitance is simply the charge Q divided by voltage. So, I put Q, and instead of dividing by this, I'm going to multiply by the reciprocal of this, times A epsilon sub naught over Q times D. Where those Q's cancel. And by putting the epsilon sub naught out front, I've got capacitance is equal to epsilon sub naught times area over distance. Or that is the distance. You understand that the voltage I'm talking about the voltage here relative to there. So this is the distance. Everybody understand that? When I'm talking about what voltage this is, right here, I'm talking about the voltage here relative to there. So that becomes my distance, D, or R in the original equation. And this is that formula we used yesterday in lab to calculate the capacitance of those two parallel plate pizza pans. Just for good measure, let's work through this example here. Example 17.8 on the top of page 484. Everybody break out your calculators, because you're going to have some arithmeticing to do. Calculate the capacitance of a parallel plate capacitor whose plates are 20 centimeters by 3 centimeters, 20 by 3.0. So we got two significant digits. And separated by a 1.0 millimeter air gap. B, what is the charge on each plate if a 12-volt battery is connected across the two plates? And C, what is the electric field between the plates? And D, estimate the area of the plates needed to achieve a capacitance of 1 farad, assuming the air gap is 100 times smaller, or 10 microns, where 1 micron is 1 times 10 to the minus 6 meters. Okay? We're going to find out why, up until recently, there was no such thing as a 1 farad capacitor. In point of fact, now they have what are called supercapacitors. I have one at home. It's 2,700 farads. And that's just unimaginably huge just a few years ago. But, okay, first, we have 20 by 3 centimeters with a 1 millimeter gap. So, 20 centimeters is 0.20 meters by 3 centimeters is 0.030 meters, keeping our two significant digits. And the gap is 1 millimeter, so that's 1 times 1.0 times 10 to the minus 3 meters. So, we calculated epsilon sub naught yesterday. Does anyone remember it? 1 over 4 pi k. Do you remember what the number came out to be? 8.8 times 10 to the minus 12, if I'm not mistaken. Wait a minute. No, they say 9 times 10 to the minus 12, so yeah, 8.8. Coulomb squared per Newton meter squared. Just in case you need to reference the units there. Okay. So, we want to know the capacitance. And that's going to be equal to the area, the epsilon sub naught, times the area, which is 0.20 times 0.030, divided by the distance, 1.0 times 10 to the minus 3 meters squared meter. Okay? What is this? 6. Did you include the minus 12 here? Oh, just this. Times epsilon sub naught. Or 52.8, which would round to how many? To two significant digits? 53 picofarads. Does anyone get anything different? You get the same thing? Everybody else get the same thing? That's right. This one right here. To calculate capacitance of a parallel plate capacitor. Why, did they use a different one in the... Oh, yeah, here. Well, we still want to keep C equals Q times voltage. All right. Well, that's A. B, what is the charge on each plate if you put 12 volts across it? Okay, well, C divided by V equals Q. So we've got 53 times 10 to the minus 12 farads divided by 12 volts. How many coulombs? I think you might need to clear your registers before you do. No, not times 12 volts. Divided by 12 volts. Q is equal to capacitance times voltage. Did I transpose that around? Yep, I did. It is. Q equals C times V. Not this. So, my bad. Q equals C times V. So, $53 times 10 to the minus 12 farads times 12 volts equals 6.4 times 10 to the minus 10 coulombs. Now, let me stop here and say this again. The C here is coulombs. It's a unit. Don't let it confuse you with this C, which is capacitance, which has units of farads. Okay? The book, they try to use italics and different kinds of notation in the fonts to keep it straight whether they're talking about capacitance or coulombs. I can't write in italics, so just keep it in your mind, keep it straight. Be cautious of this. Be careful not to let it mess you up. All right, 6.4 times 10 to the minus 10 coulombs, and now what is E? What is the magnitude of E? Let's look back over here. Voltage is equal to E times D, right? So if you want to find E from voltage, you just divide it by the distance from the conductive surface from the reference point. In this case, the conductive surface of the parallel plate. Okay. E equals V divided by D, which is equal to 12 volts divided by 1.0 times 10 to the minus 3 meters. What does that give us for an E field? Or 1.2 times 10 to the 4. And finally, let's find out how much area we would need the plate, how big the plates would have to be. If we could reduce the distance between them, D, to 1 times 10 to the minus 5, or 10 microns, meters. All right, well, we know then we want 1 farad, and that's going to be equal to epsilon sub naught, 8.8 times 10 to the minus 12 times A divided by 1 times 10 to the minus 5 meters. All right, well, multiply both sides by 1 times 10 to the minus 5. Divide both sides by 8.8 times 10 to the minus 12. And that gives us the area that we need. What does that work out to? Square meters. So it's on the order of 1,000,000 square meters. How big is 1,000,000 square meters? What's the square root of 1,000,000? It is 1,000, isn't it? It is. 1,000 meters by 1,000 meters. That's over half a mile square. If you could keep the whole thing at 10 microns apart. If you had two over half mile square pieces of metal that you could keep 10 thousandths of a meter apart, or 10 millionths of a meter, apart at every point, then you could have 1 farad of capacitance, which is why up until 10, 15 years ago, there was no such thing as a 1 farad capacitor. Of course, now we can get there because we can make that gap between them down to atomic scale. Monolayer of atoms, dielectric. But that's only been recently that they've perfected the ability to do that. Say again? Just that, by laying down monolayers of single atom layers of dielectric, where you put down like 1 atom of silicon in a lattice. That gives you, a gap on the order of 1 times 10 to the minus 10. Yeah. Even then, you're talking about breakdown voltages that, when you've only got that small of a gap to cross, it doesn't take much of a breakdown voltage to, even with a fairly significant breakdown voltage, it's not going to take too many of the actual volts. Like this 2700 farad capacitor I have at home. It'll hold, it's a 2700 farad capacitor, it'll hold a pile of charge and it will knock you in the ground. But if you put more than 2.7 volts across it, you fry it. It won't stand up. When you talk about those tiny gaps, it doesn't take much voltage to exceed the breakdown voltage. Exceed the dielectric strength. And that's what we're going to talk about now is dielectrics. There's a table here on the bottom of 485. You're going to want to make note of it. It matters. It gives you the dielectric constant K for the various materials. And it gives you their dielectric strengths. The breakdown voltage. How many volts per meter they can hold off. So, for example, if you've got air between your plates. If your plates are 1 meter apart, then you can hold off 3 million volts before it'll start arcing. You get them closer than that 1 meter apart, and your voltage is going to come down to half a meter apart. Well, you're going to start arcing at about 1.5 million volts. What you want on here is you want to know that it's here, because this is the sort of thing that if you were taking a test in class, you'd want it on your index card. If you're taking the test at home, you want to know where to find this information. Okay. Well, you're going to have to write really tiny. Like I said, you can write on the front side, you can write on the back side, you can write on the edges. You just can't write on the inside. What? Okay. All right. Split it in half. There's your index card. You split that thing right down the middle, and you get 2 insides. Yeah. I have no idea. I have seen it. Oh yeah, I've seen it done. I've seen it. People try to do it. They'll peel those corners and stick a little bit of extra right there in the middle. The back when I was in undergraduate school, I don't know, this was back in the day when everybody still had to learn how to draft with pencils and T-squares. And all of the engineering students had those retractable erasers. I don't know if y'all ever saw them. It was like a pencil, but it was like a long plastic tube that you could slide that big long eraser in and out for your drafting. Well, there was always the handful in every class that they would take all of that eraser out, and they would write all their little extra cheat notes on that eraser, and then come exam time, you could just stand out in the hall and listen to all the people looking up their cheat notes. Yeah. No, you write on both sides. You can. You can only use one side, the outside. So, the front, you can write on the front, you can write on the back, and if you can read it, you can write on the edges, but you can't split it open and write on the inside. Not in my class, but I have seen it done. Well, I mean, that's, to me, it's like, in the time and effort they put into cheating, they could just learn the material. Yeah, I know what I'm saying. At some point, it's easier to just learn the material. But, you know, I don't know. But capacitance is equal to epsilon naught times area over distance, the gap between the plates. What is epsilon sub naught? Epsilon sub naught is called the permittivity of free space. Strictly speaking, the formula for a capacitance of two parallel plates is K times epsilon sub naught times area over distance, where K is the dielectric constant of the space between the plates. No, the K from the other K is not the same. This is called uppercase K. It's the dielectric constant. Yeah. Oh, we got more than that. We throw in the Greek letters and then the Hebrew letters. I had a fun with a cop once. He told me to recite the alphabet. So I said, oh, okay. Aleph, Bet, Gimel, Dalet, He, Vav, Zayin, Ket, Tet, Yod, Kaf, Lamed, Em, Nun, Samek, Nayin, Fe, Sadi, oh, you got me. It's Sadi, Fe, Kuf. I'm sorry, you got me. He was just standing there flabbergasted. No, I wasn't drunk. I don't drink. I don't drink. I was just irritated that he pulled me over when I was in a hurry. So no. I've never taken a cop's gun. I have stolen a cop's car. But I was a deputy when I did it. So I was a deputy in Calcasieu Parish, and a friend of mine was sergeant on the police force. And one of his rookies had a bad habit of leaving the keys in the car. And so when I pulled up on a scene where he was already there, I saw his car with the keys in it. It just so happened that night I was training a new deputy who was riding with me. So I gave him the keys to our unit, said, go meet me over at the Pit Grill, which is like a coffee shop. Go to the Pit Grill and wait for me there. And I got in the cop's car and took his and drove it over to the Pit Grill and parked it in the alley behind the coffee shop. Called Billy, my friend, on his sergeant, told him where to find it. That guy. He had that guy jumping all night. Anyway. So, where was I? Dielectrics. This K is a dielectric constant. The K, the dielectric constant of a vacuum, is 1. K for air is like 1.0006, or I don't know how many zeros. Yeah, 3 zeros and a 6. So we don't really care about this decimal place in the for air, for an air gap, we'll just consider permittivity of free space. It's not likely we're going to be taking anything out to 5 significant digits anyway. And you will see that everything in the table has a breakdown voltage, except water and vacuum. Water doesn't have a breakdown voltage because it's just depends on what's in the water. Yeah. But why wouldn't vacuum have a breakdown voltage? What happens when something arcs? But what happens? Anyway, if you want to calculate the capacitance with a dielectric of, say, quartz, well, then you would multiply, you look here on this and you see quartz has a dielectric constant of 4.3, so you would multiply epsilon sub naught by 4.3 to get the permittivity of quartz. Or whatever dielectric, that is insulator, you have in the gap of your capacitor. Now, think about what happens when you put a dielectric between your parallel plates. You have your parallel plates. Like so. And you have your E field set up between them. And you might recall from the lab we did a couple weeks ago, you have equipotential lines perpendicular to those E field vectors at every point. And that's so many volts per meter that your E field, that's what's meant by when they say the E field is volts per meter. Anyway, let me get rid of those. It's going to mess things up. We got our E field here. Now we put in a dielectric. Now here they show this interim stage on part B. Does everybody see the page I'm on? On page 486. Yeah. Right. The molecules of the dielectric will start to line up with that E field. The negative, especially if they're polar molecules. The negative end will shift towards the positive plate, and the positive end will shift toward the negative plate. And it depends on the particular material. Okay? But when you put in a dielectric, like so, in general, some of the lines are going to interrupt. And the point is that not all of the E field lines will pass through the dielectric. Some of them will be interrupted. When a molecule lines up, one of the molecules of the dielectric, when it orients this way here and lines up, then the E field from the plate here is going to terminate on that charge. Okay? Now, as electrons move in that substrate or in that dielectric, as the molecules reorient themselves, to what extent will depend on the particular material, but over here you're going to end up with a molecule that's oriented this way that will then provide an exit point for that E field, come out the other side. Okay? Now, some of the electric field lines do not pass through the dielectric, but instead end on charges induced on the surface, as shown in figure 19C. That means the electric field with the dielectric has been reduced by some factor K. That means the voltage across the capacitor also has to reduce. Okay, let's make sure we get this straight, because this one is tricky, and I want to make sure I write it correctly again too. It's Q is C times V. Okay. Well, if you have this much Q on your parallel plate capacitor, with your voltage, when the dielectric is inserted, the E field is reduced. Does everyone see how that happens? Because the E field in between here goes down. But voltage is E times D. Okay? So if E goes down, voltage goes down as well. Right? So Q has not changed. Does everyone see that? The Q is still the same. We've got the same amount of charge with the dielectric as without it. The only thing that's changed is we put that dielectric in, E field has gone down, meaning the voltage has gone down. What does that mean then? If Q is still the same, that means capacitance had to go up. Okay? And yeah, this one, it takes, you got to think it through one little tiny step at a time to keep your mind wrapped around it. But this is why putting a dielectric between the plates will increase the capacitance, because it requires less voltage to produce the same amount of charge. Right? Now, real quick, let's go back to what I asked you a moment ago. Why is there no breakdown voltage for vacuum? Think about what happens when your dielectric breaks down. It begins to conduct electricity. And that's what you see as an arc, is actually, in the case of an air gap, you see an arc because what you're seeing is a plasma generated by that conducting electricity that's burning its way through the atmosphere. It's actually the atmosphere that is beginning to conduct. What is there in a vacuum to conduct? There's nothing. In open, free space, there is nothing to conduct, so there is no breakdown voltage. Now, that, of course, presumes you can get a perfect vacuum, which you're never going to do. But, say again? Even in space, you're not going to have a perfect vacuum. Up in space, you have lots of hydrogen from the stellar winds blowing. I worked on a wake shield experiment once, that ion trap that I built in graduate school for my doctorate. Was to put it. That's what they wanted for. One of the purposes they wanted was to put it on the back of a wake shield, which was think of a giant disc that they would then pull in orbit, set it going in orbit, and by putting your instruments on the back side of this giant disc, you would create a super rarefied vacuum behind the wake shield that you could never create on Earth. So up there in the wake shield, you could get down to like 10 to the minus 15 torr. Whereas here on Earth, in my lab, the best I can do is I can get down to 10 to the minus 6, sometimes maybe 10 to the minus 7 if I work really hard at it. But you're never really going to find anything below 10 to the minus 10 or 10 to the minus 12. And that's going to be very, very expensive equipment. So, but, what was I saying before that? Yeah, there's last thing for chapter 17 is the storage of electrical energy. When you charge up a capacitor with a voltage, you store a certain amount of charge on it. What you've actually done is you've created a potential. You have stored electrical energy in that capacitor. And if you really want to do so, you can think of a capacitor as just that. It's like a little bitty tiny battery that drains quickly. That doesn't hold very long. Okay? Capacitors will not stay charged up indefinitely. They will discharge. They will leak. But unlike a battery where you can actually chemically store the potential, the electrical energy, and a capacitor, it's not going to hold the charge for a long time, but it doesn't need to. If you're building a RAM, random access memory for a computer, it only has to hold the charge for maybe a couple of nanoseconds or microseconds before the next cycle comes along and refurbishes and recharges everything. But that's also why once you turn off your computer, your RAM is dead, it's empty. Whatever was loaded into memory, when you turn it off, you turn it back on, it's not there anymore. That's why you have to have permanent storage for your programming on your computer. So, the 1710 shows you the equations for how much energy is stored in a capacitor. It's 1/2 the charge times the voltage. And, of course, the charge is equal to the capacitance times the voltage, so you can also write it as 1/2 the capacitance times the voltage again, or squared. If you want to get really ridiculous with it, you can also go out and write it as 1/2 Q squared over C. On that note, yeah, I would also advise you to go ahead and read forward to the end of that, up to health effects. You'll see energy density, which is the potential energy that you've stored divided by the volume of the capacitor that you have it stored in. That's why some of these new batteries they've got, like the lithium-ion batteries, they can store enough energy density, energy per unit mass, per unit volume, that it can become quite hazardous if they fail. It can become literally an explosive, or at the very least a flammable situation. Whereas old batteries, worst you had to worry about would be spilling some sulfuric acid on your paint job. These lithium-ion batteries, they can actually burst into flames. And if they do so quickly enough, they can literally explode. Oh, that's why. It's because of tremendous energy density. Yeah. Any questions from any of the homework assignment? Anybody? I would have to trust somebody else to know that, but it doesn't look right, does it? You know why? It's got to go through the heart. Yeah, that would just skim across the top of the heart. All right, well, if no one has any questions, has everyone signed the sheet? Then I will bid y'all a good holiday weekend, and I will see you all on Wednesday.